Hello everyone and welcome back to the GoFr channel. I am Divya Darshana and today we are going to understand HTTP communications in GoFr in a much more detailed way. Now we have already discussed writing HTTP handlers in GoFr, but today we are going to dive deeper into some nuances that we did not touch on when we first got started. So let's not waste any more time and let's get coding with GoFr. As we have already discussed in our previous videos, GoFr's context is an object injected by GoFr's handler which contains all the request-specific data. For each request-response cycle, a new context is created. This request can be an HTTP request, gRPC call, or any pub/sub. GoFr's context also embeds the container which maintains all the dependencies like databases, loggers, HTTP service clients, and metrics manager. This reduces the complexity of the application since users do not have to manage the dependencies manually. In our previous video, we saw how to access different data sources through context. And in this video, we will understand handling HTTP requests and responses in a much more detailed approach. GoFr's context helps us to access different parts of HTTP request in a very simple approach. We can access the query parameter as ID assigned as ctx.request.param, and in arguments we give the value as key. So if we have a request as /configs where we pass the query parameters as key and an ID and the name as Divya, so the ID would be assigned a value of 1, 2, 3, 4, 5, 6, 7. That is the ID passed in the request. In case we want to retrieve an array of parameters, we can use ctx.params instead of param. For example, if our request is /search and the query parameter category comes with books and electronics, so then a value that is set is an array of string containing books and electronics. Moving forward, we can also access the path parameters. This can be done using ctx.request.pathparam, and then in the arguments we pass the value of the key. Last but not the least, we can also retrieve the host name as ctx.request.hostname. GoFr also allows you to bind the incoming request body in your defined entity using the bind method. So all you have to do is define an entity. Let's say that our entity is product that has the fields name and category. Name and category both are of string types and they have JSON tags of name and category in lower cases. Then in our handler, we create an instance of product and then call ctx.bind, passing the reference of the created instance of a defined entity. ctx.bind also helps us to bind multi-part form data or URL encoded form data. For this, our entity defined should be tagged appropriately to map the form fields to the struct fields. Middlewares allow us to intercept and manipulate HTTP requests and responses flowing through our application's router. They can perform tasks such as authentication, authorization, caching, etc. before or after the request reaches our application's handler. GoFr provides inbuilt course middleware to handle course-related headers. This middleware allows us to control access to our API from different origins. It automatically adds the necessary headers to the response, allowing or restricting cross-origin requests. Users can also override the default response headers sent by GoFr by providing the suitable course config. Authentication is a crucial aspect of web applications controlling access to resources based on user roles or permissions. GoFr offers various approaches to implement authorization, that is HTTP basic auth, API keys, and OAuth. Basic auth is the simplest way to authenticate your APIs built on HTTP protocol authentication scheme that involves sending the prefix basic trailed by base64 encoded username and password within the standard authorization header. To implement basic auth, you can use enable basic auth that takes username and password to configure GoFr with predefined credentials, or you can pass your custom validation function by using enable basic auth with validator that takes a validation function. This validation function takes a username and password as arguments and returns true if valid and false otherwise. In case of API keys, again Gophr offers two ways to implement it. That is the default validation, which can be selected using enable API key auth and then passing the API keys that are allowed. Or again, you can use a custom validation function by passing the function in enable API key auth with validator that takes a validator function. This validator function is API key validator that takes an API key and returns a bool value for validating API keys. In case of OAuth, we use OAuth 2.0, which is the industry standard protocol for authorization, focusing on client developer simplicity. It involves setting the prefix bearer trailed by encoded token within the standard authorization header. Gophr supports authenticating tokens encoded by the algorithm RS256 or 384 or 5112. To enable OAuth, we can use app.enableOAuth that takes a JWKS endpoint and a refresh interval to configure Gophr with predefined credentials. Now we have talked about coarse middleware as well as different authentication methods available in Gophr that helps you skip the process of writing your own middlewares while developing applications in Gophr. However, there might be cases where the users might want to add their own middleware processing before sending the request to the Gophr handlers. To fit that use case, Gophr allows you to add your custom middleware by passing it as an argument to the useMiddleware method on an initialized app instance. In traditional Golang HTTP handling, developers need to manually write headers and metadata using http.response-writer, often leading to repetitive code. Gophr enables adding custom HTTP headers and metadata using the response struct, significantly reducing the overhead of managing these details explicitly. The custom headers are defined as key value pairs of map of string that can be useful for sending security policies, debugging, and versioning. And the metadata provides optional contextual information. The common use cases are setting up deployment environment details, request tracing, and timestamps. So now that the response that we return is of response.response type, which has three fields, that is the data, the metadata, and the headers. In data, we send the normal data. In metadata field, we pass the metadata variable, and in headers field, we pass the headers variable. Now let's check our response. You can observe that we get the data as well as the metadata in response. Notice that when metadata field is omitted, the response defaults to the normal use case, that is having only the data field. In standard Golang HTTP handler, responses must be manually encoded using the json.marshal and then written to http.response-writer. Gophr simplifies this process by letting you send any kind of data that you want without these additional steps. By default, Gophr wraps a handler's return value in the data field. However, we can override this behavior for raw responses by using response.raw while sending our data. So in our use case, if we send our data using response.raw, then if we observe the response in Postman, we can see that we get the raw response. Not only this, manually managing HTTP status codes in Golang requires additional logic, often leading to inconsistent implementation across your application. However, Gophr automatically assigns HTTP codes based on the request type and the response content. For example, if we are sending a post request and it successfully creates a resource and returns a data, a 201 status code is set, and when a post request is successful but it does not return any data, then a 202 accepted status code is set. 200 is for all other general success responses, 204 for successful delete request with no content, and many more. We have discussed the status codes that are set in case of success cases, but Gophr also provides a structured error handling approach to simplify error management in your applications by including predefined HTTP and database errors as well as the ability to create your custom errors with additional context. Gophr's HTTP package offers several predefined error types to represent common HTTP error scenarios. These errors automatically handle HTTP status code selection. For example, error entity not found represents an error due to a not found entity, This error also sets the status code 404 automatically. To use these predefined errors, we would first need to import the Gopher's HTTP package, and then we can assign variables as these errors by importing them from the HTTP package of Gopher. Not only this, we can also specify database errors in Gopher by importing them from the Gopher's data source package. Now, there might be use cases where we might want to define our own custom errors. So to build custom errors in Gopher, we can declare our own custom error type and then implement the interface implemented by Gopher's errors that have methods error as well as status code. We can also optionally define a log level for our error using the log level method. And with this, we come to the end of this video. In this video, we have explored request and response handling in Gopher along with middlewares as well as error handling for HTTP communication. As you might have observed, Gopher reduces boilerplate code while following best development practices, making API development more efficient and maintainable. But handling HTTP communication isn't just about writing HTTP servers. It is also very crucial to manage inter-service communications across different HTTP servers. Stay tuned, as in the next video, we'll dive into how Gopher simplifies inter-service HTTP communication, helping you build scalable and well-structured microservices. If Gopher has piqued your interest, don't forget to like, subscribe, and share this video with your peers. Explore our open source code at github.com/gopher-dev/gopher and check out our official documentation at gopher.dev. Thanks for watching, and I'll see you in the next one. Until then, happy coding with Gopher.